Okay, so the idea is that you study the next section at home before the next lecture, and I'm going to help you a little bit by just talking you through the notes. So some of this stuff here that we should be okay with, for example, that force has units of newtons, and look, there's the first Mars bar award. That N should be a big N. Mr. Newton should have a capital. So units are measured in newtons. Forces can come in various forms. They could be a surface force, concentrated force, distributed force. So concentrated force, as if I'm applying a force at a particular point. Distributed load is where I'm applying the load over a section. And my beams are all going to be two-dimensional, so I'm kind of working pseudo three-dimensional. So my distributed loads will be, for example, newtons per meter, when in actual fact it should really be, if you think about it, newtons per area. So we're considering the fact that we've got per unit length when we're dealing with our problems. Then there's body force that you could apply, and then these what I'm calling the support reaction, and I commonly use the expression reactions, and reactions are actually forces, so they're external forces, but they are in response to some load which creates a force, and then the reaction will create an opposing force so that the object doesn't move. We did quite a lot in week 1 about moments, so we should understand this concept that we've got a force here, a distance, about a pivot point located, and that will create a moment. And I'm going to go, for this particular course, I'm going to use that going clockwise is going to give me a positive moment. Algebraic sum of moments. So moments is probably an important thing to look at, because if we don't have the moments all adding up to 0, then there's going to be some rotation of my body. Now this is not going to tell me the whole game here, really, because we're saying that the parallel forces in couples. So what we're saying here is that we can have one force going in this direction, and then we're going to have another force going about this distance away and going off in this direction here, and that would be an example of a parallel set of forces that form a couple. So when we add up the forces, so we've got a force going off in this direction, and here we've got a force going off in this direction. When we add up those forces, sum of the forces equals 0, but obviously we're going to get a rotating, spinning thing on the body. So that's what a couple is. Resultant of forces, so when we add up all our forces, then we will get how the forces are going to behave. So if I have a force going in this direction and another force going in this direction, I can sort of take this force in this direction, stick it on the end and add it to that force. And if I know where the center of mass is, I can apply that resultant force to that particular point, and that will have the same effect as if I have those two forces split away. Okay, so that's why we're doing resultant forces. Now we spent quite a bit on this, hopefully, so we should know the basic trig. I like to use cos theta all the time, so I've got this force going in this arbitrary direction, and I want to resolve it into two components, a force going in the x direction and a force going in the y direction. So to resolve it in the x direction, remember, it's always swinging through the angle. If I've swung through the angle, then I want to use cos, and that's why I like to use cos all the time. So let's say if this is 30 degrees, I'd work out that this is 60 degrees, and my calculator, I would use cos 30 degrees down in this section, and then I would use cos 60 degrees down in that direction. So I'm not confusing myself between using coses and sines. You can use causes and sines if you want. There's no law not to. We're engineers. We're not. We want the right answer. We're not so bothered about the methodology of our maths of how to get there. Okay, so that's one thing to resolve the components. And how would you find the magnitude if I knew the components? Well, I would use Pythagoras. How would I find the angle if I knew the components? Well, I'd use some basic trig. You find that on your calculator, arctan. So on your calculator it looks like it looks like tan with this inverse -1 there. So that's a bit misleading. It's actually an arctan expression that you're doing in your calculator. So for our body not to move, because our bridges and our beams and our frameworks, whatever, we're not going to have them move. So we could have called this course not stress, but statics. So meaning that we expect everything to be static. Which would have been a nice thing to call the course actually, because it would then give you a sort of nice symmetry with dynamics. So statics and dynamics, but statics is all really centering on, and if you get employed at Airbus, Rolls-Royce, whatever, you would be a stress engineer. They would call you a stress analyst or a stress engineer, so that's why we're using the word stress. So what we need for our frameworks, our bodies, we need all the forces to add up to 0, so that means that it won't move in a translational sense, and we want all our moments to add up to 0, so it won't rotate. Now, because we're working in 2D, we only really need this set of, let's look at this. So we only really need these forces, and that we could treat this as a vector. So we can, because we're going in a clockwise sense, this kind of resolves down to here. So we've got forces in the x direction, forces in the y direction, and then we're going to resolve moments around a pivot, which will then pick up my moments in the x and my moments in the y. So that will be the other component, I guess, anyway. I'm thinking actually, would it be the z axis that you're looking there? Anyway, it doesn't really matter. So we're for 2D, we're looking to basically solve 3 sets of equations here. Yeah, okay, so I was talking rubbish there. So as I said, we're summing those forces there in the x and the y, and then we're also summing the forces as if it was in the z-axis. So we're rotating around the z-axis, which is going to pick up those moments that is going to be in the xy plane. So this is what we're looking for. We're looking at solving these 3 sets of equations, and the next thing that we need to do is be able to take our free body, to create free body diagrams, and you do that from what they call, don't mention it here, but they call them space diagrams or configurations, illustrations, whatever. Doesn't really need a technical word. So basically what the engineering drawing looks like, and then we create this into a free body diagram, which just involves forces. We might indicate some lengths on it and whatnot, and how we expect the forces to behave. Part of this, creating the free body diagram, we'll see things where we imagine that a beam is on a roller, which seems a bit of an odd thing to do. The reason for this is mathematical. I don't really want to go into the details here. So this is the same sort of thing. We've got a little roller here, but we've got the sort of beam attached to it. So it's just doing the same thing, principle. And in this particular case, that means that if you apply any force in the x direction, the beam will move across. So therefore we can't have any force in the x direction. We can only have a reaction or a force going off in the y direction. In this particular case here, we would imagine that we've got some, in effect, some sort of hinge. We're kind of pivoting on a surface, and we're saying that particular contact point won't shift. There's friction or whatever keeping it in place there. So there must be some force going in the X direction, and because it's pushing down into the plate there, we imagine that there's going to be a force going in the Y direction. Okay, if that plate was now smooth, then again we wouldn't be able to have any friction in the X direction, and in which case we would only have a force going in the Y direction. Here we've got some kind of hinge, so what you've got to imagine there is that you've got a fixed hinge to a surface, and there's a pin joint going through your beam, which is then in contact with the hinge. So as you try and pull your beam away from the hinge, there will be a force opposing as it pulls away. So that means that we could have a force in both the X direction, or we could try and pull it away in the Y direction. So we could have a force pulling it away in either direction here. This particular case we won't be considering, so but the other final case is we could imagine a cantilever type problem. So this example here I've done a video on, so check out that video, work through the problem yourself at your own pace. Then there's a work solution. So the work solution, there's a PowerPoint video on that. So again, have a look at that PowerPoint, work through the problem at your own pace. Whoops. The problem sheet 1, what I would like you to do is skip it for the moment, maybe look at sort of similar problems that you can find, but that's what I want us to do in our tutorial for next week. So next week it will be, can you solve these problems? If you have, you might want to do it before your tutorial. Can try and find you other exercises to do, your tutor, if you got other problems, but I would save this for your tutorial. But these are sort of problems that you're going to be doing, and then we can work with others as you get them done. This problem here I've posted, so I've gone through a worked example. I've worked through that using a whiteboard solution, and you can look at my whiteboard solution, try and work through it at your own pace, and see if it compares with the notes. Work solution 2 again is up on the internet, so that's a PowerPoint presentation for you to look at. And then finally we've got the problem sheet 2, which again will be for your next week for you to work in your tutorial. Okay, so there's these various other videos for you to go and watch, so there's very little reading for us to do, and this is what we will be looking at for the we'll start on that the week after. Okay, so that's straightforward, not much work to do, I think.